last session, we discussed about implementation of some algorithm in Scikit-Learn. We saw how we can implement perceptron in Scikit-Learn. We saw how we can find accuracy, we also discussed putting it all together here. And you need to import everything you need. Here, download the data set or whatsoever, split your data set, standardize the data set, and now do the classification, fit in the data, and make validation and find classification accuracy. So this is basically what we need to do there. Then we said, okay, we go to another one, which is called logistic regression. And logistic regression is basically another algorithm that can be used to do classification. And we saw the implementation also of logistic regression. So here, for example, here, this is how we implement logistic regression via scikit-learn. So you can see here we import logistic reg, and now we have some kind of C, which is regularization parameter, and we have this some kind of parameter, and we plot that. So that's how we do the logistic regression. So today we're gonna see another algorithms, I mean. But before that, let's to discuss one important thing, which is regularization. So what is regularization? So we know in machine learning, you can train machine learning algorithm. It can have some problems. Number one, it can have what is called underfitting, and it can have some problem which is called overfitting. And what we want basically is something that a good compromise, something that does not underfit. So when we say underfitting here, we can see here we have our data set. We want to do classification, but the classification is not well, right? Because we can see some point are here, and this rate is in this side, so it's not classified very well. This is called underfit, right? But what about this guy? So this guy, you can see that it fit the data very well. It separates it very, very well, right? This is called overfitting. But the good thing is we can have a good compromise. Like you can see it separate the data, but only one is missing. So this is okay. Now, what is the problem of this? So when you train your machine learning algorithm using training data, and when the model performance underfit, then since it's underfitting, then naturally it will not do any good on test data because it does not fit the training data. So how can it do well on the test data? And in machine learning algorithm, we always want to generalize. What do you mean by generalize? When you train your machine learning algorithm on training data, generalization is when you test the algorithm on test data and you can see it achieve good performance. So we can see here also the algorithm here on training data overfit the data, like it learns the data very well, meaning it capture every stuff. So this one is overfitting at the training, and it overlearn, and it may not work. It may not generalize well on the new test data. So in a nutshell, in machine learning, both underfitting and overfitting are problem that we don't want. What we want is good compromise. So now how can we avoid this underfitting and overfitting in machine learning? So for us to avoid underfitting and overfitting, to just have some kind of better stuff, is we have what is called regularization. So yeah, so regularization in machine learning, where a model regularization is common problem in overfitting is common in machine learning, where a model performs well on training data but does not generalize well on unseen data. So you can see this is a problem of overfitting. So this is a training data, and we can see the algorithm classify the data very excellently, right? But it will not generalize on unseen data, which is it will not generalize on test data. That is what we mean by generalize. It will not perform well on the test data. So if model suffers from overfitting, we also say that the model has high variance. So this means that this model has what we call high variance, right? High variance model. So yeah, so which can be called by too many parameters, leading to a model that is too complex given underlying data. So a good models that have high variance are example of many machine deep learning algorithms. They have high variance because they are so powerful, complex, when you give them small data, they can overlearn, they can overfit. So such algorithm, if a model suffers from overfitting, we say that that model has a high variance, meaning that it can fit the data. Similarly, our models can also suffer from high bias. So here we can see that our model is not complex enough to capture the data. So a model that is not complex enough to capture the data is called, it has high bias. So this is a high bias algorithm, example of linear regression. They are very small, they are not complex algorithm, so they have high bias. They are not complex. So when you talk about complex algorithm, they are the one that capture many stuff. So such as deep learning, they have high variance and the complex, and less complex algorithm, just like linear regression, they are less complex, they have high variance. So now what do we want? We want a situation whereby we want an algorithm where that algorithm actually have what you call a good compromise. It's not underfitting, the algorithm is not overfitting. That is something like this. So this brings us to what is called bias variance trade-off. So you can see, since a small algorithm, which is not complex, is doing underfitting, that is high bias, and very complex like deep learning, they overfit the data, they have high variance, then we want a variance, we want to a compromise here. Like, so this is what we call bias variance trade-off. So this is something that we should know. In general, we must say that high variance is proportional to overfitting. High variance, if an algorithm you say is high variance, is mean of proportional to overfitting, while high bias is proportional to underfitting. High bias is. So now, when we talk about high bias and high variance, what do we mean in machine learning? In the language of machine learning, what do we mean? I would like to say that this chapter, if you are coming, we are doing this session, please make sure that you are reading the book, because there are a lot of information I will be skipping, and also make sure you are practicing, because when you just come and listen and go and come and listen, you will not take anything from the sessions. I mean, so it's better for us to be practicing. And also I have a code, I'm placing the code here. You can see like the setup we did, the given computer, the first code we have for chapter. Okay, I didn't upload for chapter 2. I will upload for chapter 2 and the recording, and also for chapter 3 today I will upload the recording and also this Jupyter notebook, so you can get it from there, and now you can practice and you know all those things. So now what do we mean if we say an algorithm like high variance or high variance? So in the context of machine learning model, variance measures the consistency or variability of the model prediction for classifying a particular example if we train the model multiple times. So for example, on different subset of the data set, we can say that the model is sensitive to the randomness in the training data. So for example, if we have a model like this, and now we take some part of the data, not all the data, and train the model, and now we take another part of the data and train the model, another part of the, so if the model the variability, the change we are getting while training a model on different part of the same data set, the change we are getting is what we call variance, high variance. So complex models, they have high variance. So if, for example, I have 3,000 data set, now I just split it. Maybe I just test on maybe the first 1,000. I test on the another 1,000. I train on the another 1,000. So the variability, the change you are getting, the variance, that is called high variance. So yeah, so this is what in the context of machine learning, variance means that the variability of the model prediction for classifying a particular example. If we retrain the model multiple times on different. Now in the bias measures, it means how far off the prediction are from the correct value. So that's what we mean bias. So how do we solve the problem now of bias variance trade-off, like for us to have a good compromise? How can we do that? So for us to have a good compromise here is to do what we call regularization. So regularization is a technique that allow you not to underfit, not overfit, right? So that's what we'll be doing, which is called regularization. And the regularization, the book explains a lot about what we call L2 regularization and what is called L1 regularization. So you can see regularization and this is another reason why features. Okay, so when you want to do regularization, we must make sure that we normalize our data set. So how can we do regularization? So if you look at this one, this is an example we do for logistic regression. You can see we have one parameter called C equals to 100. So this parameter C100 is a regularization parameter. We don't want our model to. So if you look at what this here, parameters, if you look at C, can you see C is default is 1. But what is the inverse of regularization? There must be positive, like support vector machine, smaller value specify stronger regularization. So stronger regularization. So small value tells you are regularizing a lot. So for example, when you train your machine learning model and you find that the model overfit a lot training data, then now you need to regularize with maybe small value. Maybe you can say 2, C is equals to 2.02. So this is a very you can small value, 2 is small value. So you are given a very doing a lot. A smaller value, you can either specify stronger regularization. And you can see here we have 100. Yeah, so something like that. So this is what we call regularization. In a nutshell, regularization allow you to solve the issue when you have your model is overfitting or underfitting. You can regularize the model so that it has a good performance to reach bias variance trade-off. Okay, any question regarding to regularization? Okay. Now let's move to another type of classifier, which is called support vector machine. Now we have seen now logistic regression. We have seen multilayer perceptron. Now we want to see another algorithm called support vector machine. So support vector machine is sometimes called SVM, and basically it uses what we call objective function to maximize the margin. So for example, we can see that this is how in the previous one, that is in perceptron, where we have a data set, we try to draw a line that separate the two data sets. So you can see this line separate this data. This is what we call a class, a line that classifies the data set, right? This is a logistic regression we saw. But now in support vector machine, what we are using is not like drawing a line to separate the data. So the support vector machine, what it's doing is this. So assume that I have data set here and I have a data set here. What it does is this. We try to find 2 point called support vectors that have a maximum distance between two data sets. So for example, you can see that here I have 1 point here, right? And I have another point here, right? And we can see that that we can see that there is what we call here called a margin here, right? And that is this from here to here. Can you see that margin? Can we see this is a margin? And we can see that here we have a line here, dot, dot, dot. It's called a decision boundary, And this decision boundary, what it does is that it says anything that is belongs here is belong to this class, that is positive hyperplane. Anything that belongs to this side, decision boundary belongs to 0, that is belong to this side. So the support vector machine is not just drawing a line to separate this. What it's doing is that it finds what 2 point called support vectors that have maximum margin. So this where this margin is maximum. So this now we get this point, this, and this, and we call this support vectors. So these are called the support vectors. That is the basic idea what support vector machine is in. So if you read the literature, you'll understand. So the basic idea is this is how we do it. Find points that have maximum margin between the 2 points. So the maximum margin intuition, you can see that the rationale behind having decision boundary with larger margin is that they tend to have lower generalization error, whereas model with smaller margin more prone to overfitting. So here you can see find between point where you have maximum margin. So this is basically the some kind of intuition behind that. But we don't need to know this. We can just call a support vector machine from Scikit-Learn. But if you want to know the theoretical aspect of that, we can follow more and see. Yeah, so you can see that dealing with nulliarity separable cases. So we'll see that sometimes the data set is not linearly separable. Dealing with nonlinear separable case using slack variable. So you can see that the data set is non-separable. So we use what we call C, which is a value. So if you look at this thing, we can see large value for C parameter, small value for C parameters here. We can see that when we have small value of C, just as I said here for this regularization, small value of C gives you regularized. So here also small value of C gives you more distance. Can you see larger value of C give you this one? So here we can see in SBM, we use a slack variable, which is commonly referred to as C in SBM. The larger value of C corresponds to larger error penalties. So you can see like, whereas we are less strict about misclassification error if we choose smaller C. So if we choose smaller C, we can see we don't consider any with strict classification error. So this C here also in support vector machine is more or less close to the C we saw in logistic regression, which is regularization. So let's look at how can we train a SBM classifier. So for us to train SBM classifier, this is how we do. We import SBC. Can you see from sklearn.sbm support SBM? Then SBM, we call this is SBC, your support vector classifier from sklearn. And what is inside this, you can see it has many parameters. So you can see parameter C, regularization parameter, which we just have shown. The strength of the regulation is inversely wise, stuff like that. Kernel. So here you can use many different kernel. So you can use different kind of kernel to calculate the support vector machine. We'll see kernel. So there are a lot of, we have gamma, we have, shrinkage, we have probability, we have cache, variable. So this means that you have a lot of parameters for support vector machine. Like as we saw now, if you look at them, like how much are they? 1, 2, a lot of them. So you may not necessarily use all these parameters to train any machine learning algorithm. But if you are doing one, you can explore and see which parameters can actually improve your learning algorithm. But at the lowest level, we need to specify the kind of algorithm we want to use, which is linear. So you can see here, SBC here, we said, okay, you can specify the kind of algorithm you want to use, like kernel, So here we say kernel and use the C equals 1, which is the algorithm parameter, and we use a random state. So you can see here, we create an object called SBC. And now if we want to feed the data, we feed the data on X trend and Y trend, right? But you remember the X trend, we use the standardized X trend data set. So here, this is what it gives us. You can see we train SBS. So you can see like training using Scikit-Learn to train machine learning algorithm is the most easiest thing. You don't need to, but here also we just classify the plot the data. You can see here I took my SVM, my algorithm. So I said plot decision tree. This is a function we define. And now I put which classifier I want to use, SVM, and now I put these guys. So just to plot this. So this is just to plotting, but this is training. So you can see now we are training an SVM, a classifier. It's pretty standard, pretty easy with Scikit-Learn. Yeah, any question before we move on? Okay, so solving nonlinear problems using kernel. So we can see here that maybe this problem is somehow linear, meaning that the data set is linearly separable. Sometimes you may have your data set that is linearly separable. You cannot separate it. So you have what we call kernel SVM. Another reason why SVMs enjoy high popularity among machine learning practitioners is that they can be easily kernelized to solve nonlinear classification problem. So this SVM can be used, as I said, to solve nonlinear classification problem. And one of the most common SVM canalize is what we call canal SVM. So let's look at how we can use canalize SVM to solve non-linear data sets. So here we create a random data set. You can see this is a random data set we just generated now here using this algorithm, the code. Now you can see this data set is actually non-separable, right? What do we mean by this? You can see that you cannot draw a single line to divide this data set, right? You cannot draw any line. So how can we solve this one? So support vector machine comes with what we call canalize SVM. So obviously we'll not be able to separate this example from positive and negative class very well using a linear hyperplane as decision boundary via the logistic regression or linear SVM. So what we use here is linear SVM, right? Because you can see the canal we use is linear SVM, meaning you are using support vector machine, but what are you using? The algorithm you are using is linear SVM. So here you can use that we canal. If you look at them here in SVC canal, that we have linear. So if you use linear, it means you are solving an issue that is linearly separable. But what about this guy that is not linear separable? So what we're gonna see is what we call canal. So how we do that is that this is the idea we use. So you can see this is the original data set. So what we do is basically this. We project the data set into higher dimensional. So you can see the data set now in 2 dimensions, right? We have Y, we have X axis, right? Now for us to solve this data set is we project this data to 2-dimensional, to higher dimensional space. So this is higher dimensional space, projection into higher dimensional space. So you can see this is higher dimension. It's not 2-dimensional space. It's higher dimension. Malama kune yan lissafi, Malama Sada. This is higher dimension. Kune yan lissafi. So you can see.
Okay, doctor.
Yeah. So we project. You can see this data set is in 2 dimensions. We cannot separate it here, but we can project it into higher dimensional space. So you can see when we project into higher dimensional space, we can divide this guy. Can you see that? We can divide it. So now when we project into higher dimensional space, in that higher dimensional space, we classify the data. Can you see that we classify the data? We land the decision boundary at higher space. Now we bring it back to our 2D. So this is how what we call canalize. So you can see this is what the basic idea behind canal method for dealing with such linear inseparable data is to create nonlinear combination of original feature to project them into higher dimensional. So a canal is a method of placing 2-dimensional plane. So you can see this is 2-dimensional plane into a higher dimensional plane. This is higher dimensional, so that it is carved in the higher dimensional space, so that you can see it is carved in higher dimension. In simple terms, a canal is a function from the low dimension space into high dimension, since we have canal trick. So this is what we call canal trick in machine learning in SVM. So we are using what we call canal trick now to solve a data set that is not linearly separable by projecting it into higher dimensional space using canal method. So now with this, we can now solve this problem using what you call canal method. So yeah. So using canal method to solve the problem, this is how we do that. So you can see here, we say SBC, the canal is RBF. So this is RBF, which is basically one of the most widely used canal is the radial basis function RBF, which it can simply be called using Gaussian canal. So you can see this is RBF. So you can see that the canal here, SBC, if we go here, what kind of canal we are going to use is called RBF. So RBF canal allows you to classify data set which is not linearly separable. What it will do, it will project the data into higher space, higher dimension, find the classification, and now bring it back to linear. Yeah. So that's what, and in Scikit-Learn, you don't bother about projecting this one to do this. The code behind this, if you specify that you are using RBF, it will automatically project the data into higher space, classify that, and bring it back. You don't need to. So this is what we said. Scikit-Learn provide consistent API that allows you to basically do other stuff. So you can see this is that. And now you can see with random state, we have another thing, gamma and C. So you can see C is a regularization parameter that we discussed, and gamma is also another kind parameter for logistic for SVM. So you can see here we create an object using kernel, and now we fit the data. You can see we fit the data, meaning we train the data, right? So here, because we are not evaluating the data to find to train on test set, because we already saw that, we are just trying to see how we can train any algorithm. So we can use the same code that we saw previously on how we can evaluate and find the performance and accuracy. So you can see here we just plot the data set. We can see now the algorithm. Now you can see try to classify this data into this. So this is basically the RBF. And the effect of other parameters you can see now here. If we change this gamma here, we use 0.1, right? We use C10. If we change this gamma parameter 0.02 and C equals 1, you can see, look at the way it do the separation. Can you see that? So you can see if we increase the value of gamma, we increase the influence or reach the training example, which leads to tighter and bumpier decision boundary. So you can see the decision boundary is tighter and bumpier, right? Unlike this one, can you see that? So yeah, so it depends on how you can see that. You can also, since we choose a relatively small value of gamma, the resulting decision boundary of the IP kernel will be relatively soft, something like this. So let's increase the gamma to 100 and C equals 1. So when we increase the gamma to 100, I run it again, look at what will happen. So we can now see that the decision boundary around the class 0 and 1 is much tighter, right? So the decision boundary is much tighter, relatively large value of gamma. Although the model fit the training data set, you can see the model fit the training data set very well. Such classifier will likely have a higher high generalization error or unseen data. So this model fit the data very well, but it will not perform well on tested. That is, it will not have a higher generalization order. This illustrates that the gamma parameter also play important role in controlling overfitting. So when we release this one, maybe one. So yeah, the model will have a generalization, will generate more beta maybe with this performance. So that's basically that. I will share this. We'll try different gamma and see how the decision boundary works. Okay, any question? Right. Now let's go to, now we have seen, go on.
Yes, using the kernel, I see that when you try this precompile kernel, it doesn't work. I don't know whether Scikit-Learn removed precompile.
Okay, what do you say? From RBF, right? RBF, this one. So let's look at it. So is it a precompile, right? We are taking, I don't know what.
Yes, there are different kernels like RBF, precompile, and many others. So
Okay.
when you use precompile, you get some kind of errors.
Yeah, so we can see the kernel. We have linear, poly, RBF, Sigma, pre-computed. So I don't know whether you mean pre-computed.
Yes, pre-computed. Yes, pre-computed. Yeah.
Okay, let's try and see that.
Okay.
Oh yeah, it gives us an error. I think this one is not like maybe removed. Maybe I think pre-computer. I don't know what pre-computer. Maybe it requires the data set to be in some format. I can see pre-computer material must be a square material. Let's see what happens. Let's go to Sklearn. Whether what is happening. Sklearn. Sklearn. Yeah, this is the kind of error. Yeah, I think the pre-computed needs some kind of pre-computed. So linear plan. Oh, I can see here they are transposing the trend data. I don't know. Xtrend, can you see this? We have Xtrend. They are creating something like this canal trend. So here, I think for you to use pre-computed, there is some kind of, I think, notion behind that. So you need to create something like this. I think, I don't know what the pre-computed, the idea behind that, but let's see it in Sklearn as well. Sklearn. Okay. Okay. Sklearn pre-computed. Yeah, I think this is this. It came in this as. Yeah, so I think I don't know the pre-computed, but I think the basic idea, as we saw in the previous example, is you need to change your, let's see, where do I see? You need to change your, is it the example I saw? Not this example, or maybe this one. Yes, so you can see here from this example, you have your data set here whatsoever X and Y set, and you have SBC canal pre-computed. And now we can see here that before you fit your data set, you must, can you see? So we have Xtrend, which is your Xtrend convert and transport. So now you use this as this. So let's look at this. I don't know if you understand what they do here. So what they do is they take your training data and multiply it by, do a dot product with it is transpose, and now save it as something called trend. And now when you want to fit the data, you use the fit. So I don't know the idea behind the algorithm pre-computed, but the idea we saw just now here for the RBF, the RBF is just basically using this, taking it to highest dimension, dividing. So pre-computed, I don't know what it's doing, or maybe it's also taking it to higher space or whatsoever. So let's look at it as well here, the example. So if we want to use fit this into using pre-computed, so maybe we need to take our trend data. Oh yeah, so maybe instead for us to use this, oh no, we have this guy, excellent standard deviation. And then STD. So this guy we can put here. So let's look at it. Okay, yes. So yeah, so we use pre-computed here. Let's look at what we on this. X has 2 features, but SBC is rating 1 over features as MP. Okay. Let me see this guy. Yeah, you can see we fit the data because the data set, I'm still using the previous data, which I didn't change. So you can see here now when you run the data, the algorithm, can you see that it works? It fit pre-computed. So the idea, I think what they are doing, I don't know the notion, the why they are using, I don't know the for a computer, but I believe you understand what they mean, right, Falalu?
Yes, sir. I understand.
But yeah, you can maybe tell us in the Slack why they are taking this dot product, where they are taking the dot product of the training set and it is transpose. So maybe you can tell us the reason why in the Slack and find out. And I don't know, like, you know what I mean?
Okay, I will check that.
Yeah, so the pre-computed, I don't know the notion why it is we are doing that. Yeah. So but now what we saw is RBS. So the idea here is this. As you can see, just the parallel will give us like another algorithm that you can use, which is pre-computed. So you need to know like how each algorithm works. I mean, if you want to use them, you need to know some parameters and other stuff. That is what make the algorithm works. So as we can see, even if you don't know, Google is your friend. I mean, you cannot know everything, right? You don't need to know everything. If you just want to find the answer, just go Google, try to find the issue. So you can see somebody already answered the same question, and you can see this is but it seems that the gram, why once you put the why okay, yeah, so yeah, so that's support vector machine. Any question? Thank you, Falalu, for the raising the question. Yeah, people may we benefit from that as well. So the next one is decision tree learning. So decision tree basically is a kind of intuitive way for learning algorithm, which is interpretable. So people prefer to use this decision tree like for when you want to interpret for the result. Yeah, so yeah, so you can see that decision tree attractive method if we care about interpretability. What do you mean by interpretability? Using this SBM, we don't know how the algorithm classified this data, and it just it's not interpretable. But with decision tree, you can draw a decision tree and show the person how the algorithm learned from the decision tree. So that's why they are interpretable, you can see. So the algorithm does this by breaking the data and making some decision. So for example, work to do. I don't know, like yes, stay in, no, outlook, sunny, some kind of decision. This is how decision tree works. Yeah, so you can read a lot, some English about the decision tree in the book. But let's look at how we can implement decision tree using Sklearn. As I told you, it's very simple to use Scikit-Learn. So you just from Scikit-Learn.3, because the decision tree is implemented under the tree class, import decision tree classifier. So you can see this one also when we try to implement SVM from sklearn.sbm import SBC. So under each algorithm, it implement many stuff. So you can see you need to know they are consistent. Everything is consistent. Likewise, when we do the logistic regression, if you go back to that, yeah, you see that. So yeah, you can see here we import this, and now we call decision tree. We create a model, and now we use some kind of parameters for decision tree. Guinea, the depth of the tree, the random set, the depth of the tree, like how many depths, 1, 2, 3, 4. These depths also determine the how accuracy the data set will be, and random state here is 1. So criteria here, what you call Guinea, which is the one that Guinea major, or what they call it, Guinea whatsoever. It is the thing that they determine to move from this direction or this direction. So they use a Guinea as a major. So when you look at here's decision tree here, we can see that criteria, we have Guinea, we have entropy, we have log loss. So you can use anyone to do the splitting. So here they are using Guinea majors to split the tree. So you can see here there are many parameters, splitter, maximum depth, the maximum depth of the tree. If not, then the node are expanded until leaves are pure. So if you you did not provide the depth, then the tree will now continue until it goes to the end where there is no any other child, which is called a pure tree. So you can see here we fit the model, that is we train the model here. So only this line we train the model. And now remember here is just we are trying to show this, plot this one to see it. So that's about decision tree. Although feature scaling may be designed for visualization purpose. So if you want to visualize some stuff for decision tree, but if we are going to use decision tree, you don't need, it's not necessarily to actually do what we call scaling, future scaling. Remember, we use future scaling in logistic regression. We use future scaling in SVM, right? Yeah, and we use future scaling in multilayer perceptron. But if you are using decision tree-based algorithm, in general, tree-based algorithm are not sensitive to, if you don't actually normalize the data, there is no issue. But remember here, we do normalization at this point. Normalization. Yeah, so yeah, I think this one go. Yeah, normalize, standardize the data. Can you see we standardize the data here? we standardize to put it in. So if you are working with decision tree, even if you don't standardize the data, there's no issue. So what meaning that decision tree, they are robust to the kind of data you have. Right. So okay, so here you can see we train a decision tree and now just show it. So now you can also, one good thing about decision tree, as we said, they are very explainable if you want interpretable result. So now you can import what is called tree. This tree is now a class that allows you to plot decision tree. So you can see we import tree. Now we give some features here. These are the features, and now we tree.plot tree. So this is a function from under tree that you need to pass the model, tree model that we train here. You can see tree model that we fit in. So we pass it, and now you pass the features you have for your data set that you train. So this data set that we train this model, you remember it is the data set that we showed previously for iris data set. So here we give the full feature, and now we said, okay, now fill true. So we run this guy, and this guy will now show us the decision tree, how the decision are been taken. Yeah, so you can see here it's calculating some kind of Gini, sample whatsoever, and now it's trying to find the, yeah. So this is something just interpretable to allow you to show how your model do classification. Then finally, we can see that you can also combine weak learners and random forest. What we mean by this is that we can see here we just use decision tree. We call a decision tree, and now we do that, but we can combine weak to strong learners. What we mean by this is combining weak to strong learners is that we have what is called ensemble learning algorithm. So if you want to do machine learning, the algorithm that works best, that even compete in Kaggle, that win competition, they are ensemble algorithm. What do you mean by ensemble algorithm? We have what we call Bayesian and boosting, and they will be discussed in chapter 7. But the main idea of ensemble algorithm is this: you can see combining weak. You have multiple prediction. So you can see here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, and you make each tree to make prediction, and you take the majority of one. So you can see here we have this guy say prediction is 1, 1, 1, 1. This guy is say 1, 1. So 6, they said the prediction is 1, but only 2 say the prediction is 0. So you can see you can take them the majority board, which is you can just say prediction is 1. So this is the idea of what we call ensemble, and we'll discuss more about it in chapter 7. But here we'll discuss what we call random forest algorithm. So random forest, what it does is that instead here we can see decision tree, and this decision tree here only create a single tree like this. Decision tree only create a decision tree, one decision tree. But what about, can we have 8 decision tree? We each one do prediction, and if we have 8, then we take the majority voting. So if I have 9 decision tree here, now I take which one, the one with majority voting. So you can see random forest is the one. It's a decision. It's an algorithm based on decision tree with many trees. That is why it is called random forest, with many trees in the forest. So random forest, like the name implies, consists of a large number of individual decision tree. Can you see that? Individuals that operate as an ensemble. Each individual tree in the random forest spit out class prediction, and a class with the most board becomes our prediction. So this is somehow a random forest. A large number, so this is it, which is true. A large number of relatively or related model operating as a committee will outperform any of the individual constituent model. So for example, I said kin yawa ya fi sarkin karfi, right? So idan mutane ana so a haɗa kuɗi, so wani kawai ya zo ya ce ayi bajinta ya bada 100,000. So sai kuma muna da mutum guda 1000 a wajen, kowa ya bada 1,000. Kaga kuɗin da za a haɗa. So what I'm saying shine, in a nutshell, ensemble method always outperform an algorithm that is not that are not ensembles in some ways. So yeah, so how can we train a random forest? So for us to train a random forest, we just call this, can you see that, from Scikit-Learn from Sklearn the example, import random forest algorithm, and now we import random forest, and now we create an object. Now first the parameters, we said n estimators, random set, n jobs. So what is n estimator? The number of trees in the forest. So you can see you can have as many as possible. So random forest, you need to specify the number of forests you have, trees you have, and random set is one. We always have random set to make our stuff reproducible. And now number of jobs. So here the n jobs is a parameter saying I'm using two multiple cores. So because like you are creating multiple forests, if I'm creating 1,000 forests, it means I'm creating this forest, I'm creating this, I'm creating. So if I can parallelize this into multiple cores so that it can be faster, that is why you can see random forest has parameter called n jobs. That is, if your computer is having 2 CPU or 3 CPU, then run them using those, utilize the CPU so that it will be faster. So you can see after we create the object, now we can feed the data using X-train and Y-train, and now we can float. You can see here, because we are using decision tree, you can see we use X-train and Y-train. We didn't use the X-train with the standard deviation, the one with normalized. So you can see, I think also here, while we do this guy, you can see X-train. We use only X-train and Y-train. We don't use the one that we standardize. So as I said, decision tree are not actually affected by your data if it is. But if you go to support vector machine, you can see when we want to fit, we use Xtrain standardize. That is the Xtrain that we standardize, right? So yeah, so you want to train the support vector random forest classifier. You just run this guy, and now we can see random forest classify this guy, which is awesome. Then finally, we have what we call k-nearest neighbor algorithm, which is basically another algorithm that can be used to classify for classification. But the k-nearest neighbor is basically a lazy algorithm, as they said. It's different from other algorithms we saw previously, and it basically has some steps to do classification. How can it do the classification? So the k algorithm is fairly straightforward. I can be summarized in this step. Choose the number of k and distance metric. K nearest, because it is called k nearest neighbor. So for example, I want to classify a point here. I don't know which class it belongs. Now, how can I do that? The first thing is choose the number of k and distance. So what is the number of k? How many k? Now I choose the number of k here. You can see you cycle. So here, this is the point. You want to see which class it belongs. So you say, okay, you want to use k equals to 5. So you will cycle the closest 5 point around to your point that you select. So you can see I have 1, 2, 3, 4, 5, the closest one, right? And now you choose the distance matrix. So choose the k, how many items, and distance matrix, what you measure the distance between here and here, here and here, here, and that is the distance matrix. Now, find the k nearest neighbor of the data record, and we want to classify. Find the k nearest neighbor. So here you can see, now after I select the k number of k and distance matrix, now I said, okay, how many neighbors? So here I have this guy, I have 1 for plus, I have 1 for 0, I have 3 for this guy. Now assign the class to the majority level. So here you can see we can assign the class to, which class do you think we can assign the level to?
Class dignitary.
Yeah, this one. So we can predict that this is class. So this guy, so this is basically what k nearest neighbor means. K nearest neighbor, how many neighbor do we have in this? So that is what it's called, k nearest neighbor. And you can see that it's pretty simple. So how can you do that in Scikit-Learn? Still the same thing, very easy. Just import your classifier. You have your object. How many numbers, nearest neighbor you have? 5. P equals to 2. Metric, the distance you're going to use to measure the distance is Minkowski distance. So if you look at k nearest neighbor, what are the neighbors? N neighbor by default is 5. So you may even don't provide this, but by default is also 5. We have a lot of other stuff. Yeah, you can see here we have metric, Minkowski by default. Yeah, so this is it. And now you fit, because we have KNN and create the object. Now you've trained your data set, and k nearest neighbor also is affected by standardization. So you can see here we use STG, that is the one we standardize. And now we train the model, and now we feed the data. You can see it does classification. So that is about k nearest neighbor. But what I want to emphasize is that this Sklearn has a consistent API. So let's look at a cheat sheet I saw here on the internet here, so that if you want to do, maybe you can, yeah. So this is a cheat sheet. So what we mean by a cheat sheet, just basically something that allows you to remember how to do a lot of stuff in Scikit-Learn. So you can see here, this is a basic one that you can have a quick look. Anytime you want to do Scikit-Learn, you need to import your stuff, like for pre-processing, for model selection, for trend test split, for accuracy. And now this is how you load the data set that we saw the example. This is how you do trend test split. This is how you can do standardization to feed your data. You can do scalar transform, and now you can train a k-nearest neighbor, and you can feed, you can do prediction, KNN predict, and now you can find score. So you can see here a basic example here of training a Sklearn algorithm using k-nearest neighbor. So there are a lot of how can you load the data, how can you train it and test, how can you divide your training data. This is it from Sklearn. Why this X trend, X test, Y trend, you call this function trend test split. Put your X, that is future false, Y the target, and put random test. So you can see this is something that whenever you forget, just quickly. Model fitting, how do you fit the model? When you create an object, you do this fit, KNN fit train data and Y trend, and this is for what do you call logistic regression for KNN, for SBM, still the same thing, right? And for prediction, how do you predict? You just call a predict your object and predict, and use the test set right here. But also you can use if you want to see probability, you can say predict underscore prob, and now give this. So this will give you the probability of the classes. It can say, okay, this one is 0.8, this is 0.9, but the one with highest probability is the expected one. So if you want to see probability, you can use this function. As we saw, if you want to predict the class, you can use this function. Yeah, so this is something that is handy, that if you want to, for example, for standardization, this is the code. You call it the scalar, standardize, for normalization, this is the code, we haven't seen encoding, but this is how you can do encoding. We'll see it, input missing value if you have. Create your models. So how can you create a model in Scikit-Learn? You just specify this. You want to create here for logistic regression, linear regression, import linear regression. You create an object LR linear regression, and for support vector machine, this is how you do that. For naive Bayes, this for KNN, this is how you use it. So you can see this is what you call cheat sheet. So a cheat sheet is basically a summary of some stuff you have that you can quickly reference. How can you find classification error to evaluate your proposal model, accuracy score, classification report using what you call it, classification report that is called confusion matrix. We have confusion matrix and regression matrix, because you remember, if you are using classification, the matrix is different from regression matrix. So if you are using regression, your matrix will be like mean absolute error or mean square error or R squared. If you are using classification, you can have accuracy score, classification report, and yeah. Okay, and we come to what is called cross validation as well. You can also tune your model using grid search and random parameter optimization. So this is something really that it will be handy. You can download the PDF and reference it anytime you find it, you forgot something to do in Scikit-Learn. Yes, so okay. So we now see that we understand different kind of machine learning algorithm that are used to tackle linear and nonlinear problem. And we also see that decision tree is actually a good, and it allows to do some kind of interpretable prediction. Also, SVM are powerful near model that can be assigned to nonlinear via canal tree. They have many parameters to be tuned in order to make good prediction. So here you can see that SVM, because it has many parameters to be tuned to make a good prediction. So this is one of the issue of SVM. So let's look at it. So parameters, what? So let's look at how many parameters SVS. You can see it has a lot of parameters. So these parameters, you need to tune them, like substitute, put another one, select another one to make a good prediction. So one of the disadvantage they said for support vector machine here. In contrast, ensemble methods such as random forest don't require much parameter tuning and don't overfit easily decision, which makes them attractive. So you can see that random forest that we just saw, one good thing with that is that it does not require many parameters. So if you see this random forest, it does not require, as I said, many parameters. So here we have n estimators, and yeah, so but the one good thing is that random forest does not always overfit, which is really good. Can classifier offer an alternative approach to classification via lazy learning that allow you to make prediction without any model training, but with a more computationally expensive prediction step? So you can see K nearest neighbor is not doing prediction, right? But rather what it's doing, K nearest neighbor, it's just looking at the close proximity. Why I could near pure in belong to the online classes. So you can see that it's not doing any prediction, but rather finding what is maximum K nearest neighbor in that. So that's what the point they are doing. In KNN classifier, it's okay. The KNN classifier offer an alternative approach to classification via lazy learning that allow us to make prediction without any model training. So you can see without any model training, you can make prediction, but with a more computationally expensive prediction steps. However, even more important than choice of appropriate learning algorithm is the available data you have. So whatsoever any algorithm you're going to have, whether the algorithm is the best algorithm, the first thing is your available training data. No algorithm will be able to make good prediction without informative and discriminatory features. So there is no any algorithm that will make a good prediction if you don't have a good features in your data. So in the next chapter, we will see how we can create a good data set and for our machine learning algorithm. So that is about what we have for today. And as I said, I will upload this stuff here. And when I upload it, you can have access to that. And yes, yeah. So what I want to give you is this example. Please go and try to implement this. This is SBM classifier tutorial. Do it yourself and see, follow it from beginning to the end. And now you will learn a lot about this tutorial. And that is basically how you can do Scikit-Learn to implement it from the beginning to the end. So I will share this one as well. That will be our assignment for next week. In next week, I will expect each one of us to be able to present training to train a classifier here. You can see it's everything explained. And the code is there. What I want you is just to run the code, learn, know how it is done. For example, here you can see they even do exploratory data analysis. They see how many data sets you have. So that's what I want us to do. So please go through this one, go through it, and I will expect us to present this information to all of us. Any question? Falalu, do you have any assignment that I say you should look up for us? I don't have time to look up anything. Okay. That's like. Okay, let me check it.
The link should be in rather than the.
Okay. Cool. Okay. Right. So let me open it. So let me call it practice. So we can have a folder called practice. Co-project, maybe project.
Ko assignment.
To assignment nake baka?
Mana.
To ni malamin ka ne zan baka assignment?
To da me?
Ni ka. So ba malamin ka bane ma. So let me import it. Well, yes, anyway, okay, just wait for me. Doing something. Oh yeah. Why naga yake somebody? Yeah, so there is another thing, the okay, document via score. Machine learning. Okay, projects. Okay. So you can see here, right? Okay, and I can come on a formula. Okay, so Palalu, can you explain what this is all about?
Yawwa, kamar yadda ka yi bamu in muka duba peji na 20, ya yi mana bayani akan decision function haka, wanda kake maganar cewa yana karɓar irin kamar irin value haka, sai returning din idan value da sai comparing idan value din is greater than or equal to 1,
Okay.
sai returning 1, otherwise sai returning 0. Haka. So a wannan exercise din shine we are required to create a function. Okay, ashe na ma ina turo da shi. So irin wajen blank zai zama kamar nan zai zama blank haka. Sannan kasan nan wajen return din nan babu komai a ciki, saboda haka mu ne za mu yi function din sai mu yi implementing din function din da ƙarshe sai kuma za ka yi mana irin wannan kamar a start din. Idan mutum ya yi daidai komai function din
yeah.
automatically zuba da tick a cikin.
So here we can see, yeah. So we can see here we can use assert to check whether the decision assertion is true or not. So anyway, catch it, so yeah. So no worry. So what Falal did here was basically, remember we talk about decision functions that shows if z is greater than or equal to 0, the classification is 1, if otherwise it's 0. So what he does is just a function here we have, and given the z whatsoever the value, return 0 if what if z is less than 1, return 0, but if z is greater than sorry, yeah, if z is it's less than 1, return 0, right? But if it else means it's greater than or equal to 0,
greater or equals to,
yeah, then you return 1. So this is just a function. So here it's just like what we call assert, which we if you know, which basically check to confirm if something is true. So you can see here we call assert decision function, which is this function here. We have the input, which is z, so we say is 5. Now the result we said equals to 1. Is it if we have a 5, what will be the result? Greater, if z is greater than equal to 0, greater than equal to 0, the result will be 1. So here is 1 is correct. So here we are trying to check whether this is true or not. So if it is true, it will show you it. If it is not, so if this is 0, then we consider when we run this guy, it will tell us this something fell. But when we have is 1, so yeah, it shows that that's correct. That is true. So yeah, so I think what I want to give us to go and try to see is this tutorial. Just go through it yourself, follow it along. I can see that it is well, it has a lot of stuff and a lot of comments. It means the tutorial is good. I mean, people like it. So what I want us is just this is cargo. Just follow it. Implement this stuff in your computer, your algorithm. I mean, I don't want this explanation. All this explanation, read it and learn it if you want. What I want is just from the implementation. So you can see they provide the data set description. So you know all this stuff. Just try to see what this just to understand how you can do that. Next week, inshallah, we will do chapter 4, which how we can prepare our data set. Yes. Anyone with question? Right. So in a gaba question kenan, and it means okay. So here I shared the first one. I shared the GitHub link where Neki Saka slide. I shared.
Sorry, wait. Is there no WhatsApp group for this class?
Gani WhatsApp group. Wake up, Gani WhatsApp.
Link them by they are easily accessible through WhatsApp. That me, I'm just trying to even locate the why group then Slack Dina from computer, and I'm not seeing it only on phone.
Kai mana creating don group a WhatsApp sai mu yi idan maybe da akwai wani abu idan kana ganin is accessible.
Kai kana da kai ne ke da nambobin mutane, ni ina jin daga kai sai.
Idan kai sai ka sa mana ci a cikin abun nan group din abun nan din Slack ka sa mana group link din a Telegram sai mu shigo.
To shikenan.
Yeah. Right. Any question? Okay. So please create mana WhatsApp then so that maybe it will be a good point for discussion and people.
I mean, why not Telegram?
Okay, to duk wanda aka ce ba masala.
Yeah, I think Telegram will give a message in case if somebody join late, can be able to access the
okay.
But WhatsApp cannot be able to.
Okay, yeah, that's correct. So you mana Telegram, you mana Telegram. So wasu daga cikin wannan duka suna yin Telegram?
Sorry, ma awal sai dai kai Telegram, ni ban iya Telegram ba, serious. Gaskiya iya Telegram ba, serious, ana chat da shi.
Ni ma ba mai kawai ka gwada, kai ba malamin kwamfuta ba ne ba.
Malamin kwamfuta yanzu ya kasu ba fata a try it.
Yeah, but it's simple. Just create it. I think it's
Mala Awali mana Telegram din kai mana sharing da Allah group din saboda naga shi wannan saminin sai a hankali.
Da WhatsApp ne na iya, ma Telegram yanzu sai na zo na.
Ai ga
WhatsApp
the point din da sa Awali ya kana is really important. Maybe people da ba sa nan maybe sai abin nan. Amma kuma muka koma Telegram gaba ɗaya mutane Telegram ai chat abubuwan zai koma ba Slack ba kuma.
I think it just additional abu.
Okay,
just like WhatsApp. Yeah, Slack will remain as it is.
Okay, to Balefi. So yeah, inshallah we see next week. And if you have any question while practicing the what I shared, just let me know. We can learn all together. Yeah. So don't forget, if you don't have the book, I believe we all have the book. I keep saying read the chapters. If it is when you read the chapters and practice the content that you'll have take out many things from the curriculum. But if you don't read the chapters, you just listen, come here, you will not make many sense. Yeah.
Wait there, okay. The name of the book is what?
I can't go. Be sending it up about it. I'm gonna go. So let me share the book again. I mean share ina ji baka zuwa mana session ne, so you are listening a lot.
Yeah, I love that I attended the session yesterday. So
ai kai ne in nace ka zo sai ka ce wai ai kai baka da time.
Ba ka ce
na ga da mu baya.
Bolt ne ya hana shi zuwa ko?
To ka gan shi da Saminu?
Na ga hoto.
Hoto kuma littafi da ko?
A wani littafi oke to ai. Gaskiya da shi ka san me? I've been looking for the book da ake yi tun jiya wallahi ban gani ba, so na ce let me just ask.
To ai ba ma da. So the book we are using is called Machine Learning with Pytorch and Scikit-Learn. So the littafin yana yin machine learning, za a yi machine learning sannan kuma from chapter 10 idan muka je za a fara yin deep learning. So it's combination of machine learning and deep learning. Yeah, so I would also recommend people that are new to machine learning, please, there is machine learning Coursera na Andrew NG, sabon course machine learning from Andrew NG. I would like to maybe ask people, so it's a specialization. This is a very good course, specialization for machine learning. If you have not done so, I have done it also for the time, the day. So this is specialization. When you register for Coursera, you will do these courses, 4 courses, 3 courses in this machine learning specialization, and you will get certificate. The first one is called supervised machine learning. Even one the supervised machine learning. The second one is advanced learning algorithm. I think it discusses some kind of it uses neural network what to see in the second part of this book, but they are using TensorFlow. And the last part is using unsupervised learning, which is reinforcement learning. Malama Kenny, reinforcement learning, I think this will also be useful.
Gaskiya doctor har TensorFlow ɗin ina so.
Yawa. So what is
yana tilon course din yayi a YouTube yana
na
magana
gani
akan
a
YouTube
LinkedIn ma. So ni lokacin da yayi course din for like na tsohon course din wanda yake ba updated ba. So wannan supervised machine learning na yi wancan. So wannan supervised machine learning is very good. Samino has finished this one, the first one, supervised machine learning, and he got the certificate. Now Samino ina ji yana apply, yana second one. Kuma the good idea is ko baka da kuɗi yanzu, you can apply for this course. Now abinda ya kamata ka yi, you need to apply for what is called financial aid. So idan ka anyway, what I'm saying is that you can do this without paying. What you need is just click financial aid. When you click financial aid and write them in English, that what are you to write them? Bani da me a Nigeria ne kaza. Dinna dai duk dam student cewa kaza da kaza. After 15 days, that's to make away with a question and you get certificate at the end. But before 15 days elapsing, you can go through the course, start going through the course. But ba za ka iya yin assignment bane ba. Ba za ka iya yin assignment ba. So shine kawai. So maybe idan ka applying, kafin sa approving, you have gone through the session maybe with 1 week, 2 and finish it. I think that will also give you a good flow with the book. Andrew,
Okay.
so when you go through
Coursera ne ko doctor?
Coursera ne.
Okay.
So when you go through this one, it will give you a good flow. Like the book that we are going will be like a kind of help to learn more. But because this is a course like you will finish it in 1 or 2 weeks, you will get the idea in very short time, and the book just we are understanding more about the machine learning. So I would recommend it. Please go and sign up for the very first course. This one, supervised machine learning, and see how it's really recommended. I really recommend this course. Yeah. Okay. So Saminu, I will share the book with you. I will share it with you. Inshallah. Okay, so we are on top of the hour. Inshallah, we see you next week. Bye bye.
Thank you.